We need to discuss the next topic, which is called built-in self-test. Or logic built-in self-test. Some people refer to BIST as built-in self-test as built-in BIST. Okay. So, this is called logic BIST. Okay. See, as I may have mentioned before, chips are getting more and more complicated, right. So, as a result, the testers that are required to test them also will get complicated. See, the number of test patterns is increasing. Okay. Because the size of the chips is growing and the number of flops is increasing. Then the frequency of the chips is increasing. All these will present challenges to the test equipment. Okay. The higher number of patterns, higher number of flops would mean that the data volume, okay, the test data volume will be high. And because the frequency of the chips is increasing, it may also mean that the ATE has to be very fast to be able to supply data at such high frequency. So, that is the challenge of testing today. So, it makes sense if it is possible to, can we avoid the external tester, because it is very expensive, okay, it costs millions of dollars. Okay, that is the purchase price. In addition to that, maintaining it costs money. Training on how to use the testers, that costs money. So, in general, having ATEs is if we can avoid having an external tester, then that will be great. Okay. But how is that possible? Okay, can we avoid external testers altogether? So, there are many answers to that question, right. So, one is any test requires test pattern and then response checking. So, we should generate a test and then we should know what a good circuit will respond or how the good circuit will respond. So, for example, I might say I need to apply 1100 and a good circuit will produce a 101, but a faulty circuit may produce something else. Okay. So, we need both. Okay. Now, in logic based, they try to use what is called as random patterns. pseudo random patterns. So, let me give you an example. Okay. So, let us consider this circuit. So, this is a shift register. Now, if you are willing to take some of these outputs and if you are willing to feed it back, okay, we took an XOR gate and we fed the last 2 bits and we are feeding it back. Let us assume that the initial state of the flip flops has been adjusted to be 0 0 1. Okay. We should not initialize it to 0 0 0. So, let us assume that we have initialized it to 0 0 1. Then when the clock comes, the XOR of 0 and 1 will be loaded into the leftmost flop and the other 2 bits will shift. In the next clock cycle, again the XOR of the last 2 bits will get loaded, right, and it will shift. Again the XOR of the last 2 bits gets loaded, it will shift. XOR of the last 2 bits get loaded, it will shift. XOR of the last 2 bits get loaded, it will shift. XOR of the last 2 bits. So, it has cycled back to the original state. Okay. So, if you look at the transitions that are happening here, suppose we refer to this as the state 1, 0 0 1 is state 1, this is state 4, 1 0 0, this is state 2, this is state 5, this is state 6, state 7, state 3 and finally state 1. So, you can see that we are going from state 1 to 4, 4 to 2, 2 to 5, 5 to 6, 6 to 7, 7 to 5 and then back to 1. Okay. If you put 0 0 0 in the flops, then unfortunately this circuit will continue to produce zeros. Okay. It will remain there. So, this is a state diagram of the this circuit, which we call as linear feedback shift register. See, it is a shift register plus it has a linear feedback. The feedback refers to taking some of the outputs and then combining it in a gate and feeding it back, and in this case the gate that was chosen is a XOR gate. See, an XOR gate acts as an adder. Okay. You may know that in an half adder, we have already seen that XOR gate is a sum and carry is the AND gate. Right. So, if you do not worry about the carry, the sum is nothing but a modulo 2 sum. So, if you have 0 plus 0, the answer is 0. 0 plus 1, the answer is 1. 1 plus 0, the answer is 1. 1 plus 1, the answer is 0 because the carry is ignored. So, this is what the XOR gate does. XOR of 0 and 0 is 0, XOR of 0 and 1 is 1, XOR of 1 and 0 is 1, XOR of 1 and 1 is 0. So, the XOR acts as a modulo 2 . Okay, that is what the XOR gate does. In this example, we took a 3-bit LFSR and you will notice that the states that appeared, they appear to be sort of random, 1, then 4 and then 2 and 5. So, it appears sort of random, but if you happen to know the initial state, if you know the initial state, you can reproduce the entire sequence. So, there is no secret there, right. If I tell you that the initial state is 0 0 1, then you can say the next one will be 4, the next one will be 2, etc. So, in that sense it is a pseudo random sequence. It is pseudo random because we can predict the sequence if you tell me the seed. So, this is called as the seed. We can choose any seed except 0 0 0. I could choose 5 as a seed. If I choose 5 as a seed, the next state will be 6, 7, then 3, then 1, 4, 2 and so on. I could choose any seed. So, let us understand the idea of these linear feedback shift registers, why they are used.